Yeah, I was going to say, indeed, you can solve convex, you can optimize convex functions over convex sets,
Right.
given only a separation oracle for the convex set using ellipsoid algorithm.
Right.
Except that there are some mild technicalities.
Okay.
There's some like mild technicalities, assumptions you need to make in order for this to make sense. To give like a simple example, like, you must assume that the optimum occurs inside some potentially giant
Right.
box, even of exponential size.
Right. Right.
Which is like automatically true in linear programming, but like you have to just like literally make it as an assumption in convex programming. Now, in like most typical situations, it's true. Like, so I mean, it's
Right.
not like it's worrying you or anything.
Yeah.
But that's an example.
Right.
And there are some like other like weird, like there's like weirder issues, like if your convex set like happens to be like low, not full dimensional.
I see.
But yeah, so generally one can do this. But so I come out from like like a theory-ish perspective, and well, for most classical algorithms problems that use linear programming and 70-definite programming, this is somehow it's more or less sufficient to know about linear programming and semi-definite programming.
I see.
Yeah,
Yeah.
and linear programming especially is the most mainly is one. And there's like a nicer theory, but it's what you say is right.
That makes sense. I guess like just in like machine learning and some of the other spaces, there's more emphasis on convex kind of problems because you're like essentially trying to solve non-convex problems like NP-hard problems, and then the closest you can get is by like relaxing it to some convex problem and then trying to get some intuition on how you can solve the convex problem. So I guess like LP is like the other end of the extreme where it's like things that we know can be solved in polynomial time.
Yeah, I mean, it's the same spirit in both cases. I guess like maybe in like machine learning and optimization, it's typically a little bit more like, oh, you have like very complicated non-convex function on like a simple-ish domain, and the main work is maybe I don't know, working about like how to optimize this complicated function and replace it by some kind of surrogate that is convex.
Right.
Whereas like this linear programming stuff is more, connected to like trying to optimize over integer points, and therefore like maybe it's more like you have a simple function you're trying to optimize, but over a very complicated domain.
Right. That makes sense. Interesting.
Yeah, really, the case where you're trying to optimize a convex function, it's really not much different from like trying to optimize over a convex domain, because
Right.
like a convex function, you can consider like the set of points that are like its sublevel sets, or like all the points where it's like at most 100, and then this should be a convex set. Maybe I should say at least 100. But anyway, one of these should be a convex set, and so they're related problems.
Makes sense. Yeah. Yeah. I was just like interested because I was studying like convex optimization recently, and I'm like, wow, there's a lot of analogs between this and like LPs, but like usually like they just like kind of skip over LPs, QPs, QCQPs, like and say like directly, well, everything can be formulated as an SDP, and then we'll just work on that.
Yeah.
And then use like CVX pi or something to solve it.
Yeah, well, a little bit, from my perspective, I'm interested in explaining also like, why you can solve these things efficiently and like how. So it's like natural to maybe build up the starting from linear programming.
That makes sense.
Yeah. Yeah, we can also always, as always, discuss things that are not the homework as well, but we can also discuss the homework. Do any of you all have some questions you want to ask about?
I don't know if Ken has something. I think I like kind of have most of the homework already. but we can go through a problem.
Okay.
Yeah. How about just going through 8.1 maybe? Because that was interesting. It was like somewhat fun because I've come at it from like an SVM kind of perspective, and this kind of was similar but slightly different from the way I'm used to looking at it.
Yeah, actually, even this last part is kind of like SVM with a degree 2 polynomial
Yeah,
kernel.
yeah, exactly. So I was like, wow, like it's like forcing me to think a little bit differently about a problem, which I thought I had a lot of that I understood really well already.
Yeah, that's cool. I don't know. Do you have
But
like any specific question about it?
so for the first one, like part A, I was just like a little bit maybe confused as to that like hint, the A dot X, not the hint, but the A dot X plus B is equal to 0. Is that X the same as the XI thing, XI here? Because we were somewhat confused that if A dot X dot plus B is a constraint, then you can't explicitly like get any hyperplane, because it like kind of forces your hyperplanes to look a certain way. Like if you have a constraint that A dot X plus B is equal to 0, then your minimization will always be yi, right?
Let's see. So I mean, let's think about this case D equals 1.
Yeah.
So I mean, the way I have it in mind is, okay, here's R2, and then you get these data points. Like I don't know if there's like 5 of them. Let's see. Where's yellow here? Maybe it's like here, here, here. I don't know, here, and here. And so maybe this is like x1 is, okay, maybe this is like -3 comma -6.
Right.
But like this is, x1, and this one is y1. Maybe this is -2 comma -1 or something,
Right.
etc. You got 5 of them.
Yeah.
This is like x5, y5.
Right.
Yeah, and the
And if
task is
you,
you're trying to find like a line.
yeah.
The equation of a line is like, well, in high school, maybe you write like y equals mx plus b, but you can also say like, a x plus b equals 0.
Right. But in this formulation, X contains both X and Y, right? Like
Little x?
little x here is like A dot X plus Y. Sorry, A dot X plus B is it's like it is going to X is going to have both X and Y, right? Because AX plus B is equal to 0 is just a vertical line, right?
Oh, wait, maybe I've typed this wrong.
Yeah, that was the thing I was somewhat like we were somewhat confused about.
Oh, well, oh, yeah.
Yeah.
I've kind of typed this wrong. Okay, this is a problem. Yeah. I had in my head, yeah, that's not good. So this, I guess I meant
Yeah.
here, like, A1,
Right,
it's like
exactly.
A1 X plus A2 Y plus B equals 0.
Right.
Okay,
That
yeah,
was
this is a
that
typo.
was the
All
thing
right.
we were like confused about, because we were like, wait, this is like forcing us to like because the constraint forced us to pick vertical lines, which just like did not work in the rest of the optimization.
Oh, yeah,
And
yeah. Okay, thanks. Yeah, I spaced out. This should just, this should just be the generic
yeah,
definition of a hyperplane, which everything is happening in like, as you say, it's really happening in like D plus 1
D plus
dimensions.
one. That's right.
Yeah.
That's right. D
So this
plus one
should,
dimensions.
yeah, this should be like, this X should be kind of like X comma Y, where this is like D
Right.
dimension, and this is 1.
Right.
Okay, yeah,
Exactly.
that's confusing.
Okay, cool. Now it makes sense, because we were like confused for a very long time trying to figure out like what this constraint was and whether we like needed some like vertical line or something. But I guess then that thing just like then it's just a definition of the hyperplane with like X and Y concatenated into X, the little X here.
Yeah. Okay, yeah, I'll fix that. Sorry about that. So that was a confusing typo. Sorry about that.
Yeah.
Yeah, maybe you should just like read, if you know what the words mean, just read the words and not the
Yeah. Yeah.
not the math letters. Yeah.
Cool. So yeah, and then like I guess like then it becomes like relatively easy to like see if you just like have a generic hyperplane and not like the specific kind given here.
Yeah.
That you could just use like some variable t to be ax plus b. Sorry, to be like the absolute value, and you can have like t is greater than or equal to ax plus b, and then t is less than or equal to ax plus b, I think.
Yeah, we even like mentioned a little bit about that trick in the class
Yeah,
yesterday.
yeah.
Yeah, okay, whoops. Somehow I've used this exact problem text before and people had not noticed it. So, okay, very good.
I see. Yeah, that makes sense. And then yeah, so then I guess like the second part made sense because like we were
Oh, this
confused
you
about
mean?
the first part, but then the second part like made sense. So we were like, wait, do we just ignore like the first part because of that hint? But I guess like so now that the hint's resolved, I think we got the rest of it.
Gotcha.
Yeah. Okay. Yeah, I don't know if Ken has any questions in general, but that was like the only thing that I was like somewhat like unclear about in this homework.
Okay.
Yeah, sorry, I was in a public space. I maybe just one super minor question for part D of the first question, 8.1. So if we say have some ideas for ABC and turned the constraints, well, the things we want to satisfy into a constraint, do we in this case simply just add really the C part into the constraint and basically call it a day? Because the C becomes like a matrix, and then you can expand it, I guess, in the extra constraints for each of the rows or columns of the matrix, and then
yeah, probably pretty much. I mean, I think like once you understand what's going on, well, this is like a comment that's devoid of content, but like once you understand what's going on, like there's not too much mysterious about this problem. So yeah, I mean, as long as like maybe one little thing to think about, maybe not directly related to the problem, but you know, one thing to emphasize is that this is like still a polynomial sized LP, and you might think about like, okay, if we can do this, what about if we allow like cubic surfaces or degree 4 surfaces or whatever? You might think about like, oh, how high a degree can we allow while still keeping it polynomial size? But it's not even directly relevant for the problem, but like it's just something to think about.
So would any so it's not every kernel would work here. So this is like a quadratic kernel, but would you have like if you had like a more complex like RBF kernel or something, then it wouldn't be a QP. Oh sorry, LP for anymore then theoretically.
Yeah, so this is a good point. So it's related to what we were talking about.
Right.
Yeah, I mean, you know, the size here in the LP, like you're really like literally writing down the whole optimization
exactly.
problem on a piece of paper. And so like if the kernel is getting like more and more high degree, then like it will get, you'll need more and more paper to write it down and therefore solve it. But like we were saying, like, you know, one interesting idea and that's used in SPMs and stuff is that sometimes you can use a kernel that like, if you were to like write it down would be like high degree or maybe even infinite degree in some sense.
Right.
But depending on how your algorithm for like, you know, trying to minimize the error operates, if it like, you know, only operates on its data points by taking inner products of kernels and things, as long as you can do those operations efficiently, it doesn't matter if like writing out the kernel would be some super large or infinite expression.
That makes sense.
Yeah.
Interesting.
So it's a little bit similar to, I mean, it's similar, at least in spirit, to the idea of like solving linear programs where you don't have the linear program explicitly written down, but you have the ability to efficiently solve like the separation oracle problem. Like if somehow if you're only interacting with the set you're trying to optimize over through like separating hyperplanes, then you need not necessarily have to write down the whole, have the whole LP written down.
Yeah, that's interesting. That's like somewhat like, that's close to like how like you would think of kernels when you actually evaluate them. You're trying to, you just evaluate them on your test, on your data points, not on your like, not like for, not write it down explicitly, the whole thing.
Yeah.
Cool. I guess I could ask like just a general question
Sure.
on the duals. So I understand like, so is the dual of the LP essentially the same as like when we talk about duals in like convex op, we talk about it as taking like the Lagrangian and then solve it. Sorry, yeah, the Lagrangians and then like solving for like the Lagrangians. Is that the same thing here? Just like in a different, seen in a different way, or?
Yeah, it is the same thing. So this is, I mean, the let's say if you just simplify and focus on LPs,
Yeah,
it's the same thing, like taking the Lagrangian optimization problem and taking the dual. I guess, yeah, it's just like a different, you know, you can show they're the same thing. It's like a different perspective, I suppose, on it. I really like in this course, I really like this kind of proof theoretic interpretation of the dual, where you know, if you're trying to maximize, you know, if the primal is about maximizing something, the process of duality is to try to like construct a certificate that the maximum is at most some value by taking linear combinations of the constraints. I guess, yeah, I guess like in terms of the Lagrangian business, it kind of becomes a little bit trivial in the context of linear programming because like all the expressions are like linear functions and therefore like their gradients and things are like very simple. So once you get to like more complicated setups with like STPs and things, like the notions of duality become a bit more subtle. There are like duality theorems for semi-definite programming that basically, you know, if you're trying to maximize a semi-definite program, you can take the Lagrangian dual and it'll turn into another semi-definite program, a minimization problem that, you know, any solution to which is like a sort of a certificate for the an upper bound on the primal value. However, it's like not necessarily the case that this like strong duality holds, that you know, the best certificate that you can achieve in this way is actually equal to the true optimum.
So you need like Slater's condition or something like
that. Yeah. So like it somehow like morally holds in like many or most cases, but like there are technicalities. And so like technical cases where it doesn't hold. And actually, Slater's condition is one popular one, although like I find, at least in theory, if not in practice, it's not so useful because in particular, like Slater's condition like requires that the feasible region be full dimensional because it has to have like interior points, at least. And this is like often not true in like you know, STPs arising from combinatorial optimization. Like pretty soon we'll look at like the one for max cut where you're like maximizing something and you have this condition, you have like a matrix X of variables, and this is supposed to be positive semi-definite. And you know, some of the constraints are that like every diagonal entry is equal to 1. And you know, this constraint alone is like intersecting the whole space with like hyperplane. So like the
Yeah.
whole feasible region is in some like lower dimensional setting. And so
I see.
Slater's condition doesn't apply. It's a bit annoying though, because like it turns out that like strong duality does hold for the max
Right.
cut STP relaxation. It's true. It's just like, oh, you can't deduce it from this, like, for example, Slater condition.
I see. You have to do a little bit more work for that.
Yeah. So like this kind of theory is like a little bit tedious. You can actually, there's like even like, research papers that show you can write down like a different dual than the standard dual, and it'll be an STP and it will always satisfy strong duality.
Oh, wow.
It's just like it's much more complicated, this other alternate dual. So I think it's a result that's maybe only interesting in theory and not so much in practice.
Yeah, because in practice, I think like we usually take the dual and we like, because the dual is like easy to like kind of solve usually for some reason, I think, because it's like an easier problem. And then like from my intuition is that like the duality gap is usually the difference between like how NP hard the problem is and like being able to solve it like efficiently using a convex program. Is that intuition somewhat like correct, or do you think there's some flaws in that?
Yeah, I'm not sure. I don't really think about it that way. At least here for these things like semi-definite. Well, okay. For semi-definite programs, like the duality theory is, as I was saying, kind of like morally correct, even if it like maybe like there's some technicalities, like for the most part in like almost all like normal circumstances, like there is no duality gap. Or more or less. And this is reflective of the fact that like, semi-definite programming it's related to the fact that semi-definite programming is solvable in polynomial time.
Right.
For maybe this is what you were alluding to, is like for more general problems, even more general problems, or like convex problems, optimization problems, you can have circumstances where like maybe you don't expect strong duality to hold, and therefore there will be some duality gap. And this will be related to or indicative of the fact that maybe this optimization problem is not solvable exactly in polynomial time.
Yeah.
Yeah, what you say is true. And there's a funny thing too, is that like, for example, with semi-definite programming, assuming strong duality holds, which it usually literally does, or at least morally speaking does, including some technicalities. If you're only interested in like the numerical answer, then you can get it either by solving the primal LP or solving the dual LP. And sometimes these have like wildly different complexities. Maybe they're both like polynomial time in theory, or maybe not, but like in practice, like solving one could be like much faster than solving the other.
Right.
And well, in fact, this even comes up in theory in like algorithms for like linear programming. Like sometimes you'll see in some kind of sophisticated papers, like maybe they'll like set up an LP that they want to solve to capture their problem with the property that has maybe exponentially many variables and polynomially many constraints. And this seems bad.
Yeah.
But then they'll take the dual and they'll say, oh, the dual has now like polynomially many variables and exponentially many constraints. They have the same value. And then like polynomially many variables and exponentially many constraints, you can often solve these, or sometimes you can solve them using the ellipsoid method if you can argue that you have an efficient separation oracle.
Right.
Yeah. So this is like some.
That's cool.
Like, theoretical instantiation of this phenomenon that sometimes like the dual or the primal might be much easier to solve.
Yeah, that's very interesting. Yeah, because like that's the intuition I had for why like people care about the dual usually, because one is usually the dual. I mean, at least when I studied like SVMs, like they claim just the dual is super easy to solve, so you just work with the dual, and then like you reason about it with the primal. And yeah, there's some dual, like that you could still talk about the dual, like in terms of separation gap and margins and stuff, but usually we talk about like solving the primal, but primal's so hard to solve, so you convert it to dual and then you solve the dual, and the dual is like super easy.
Yeah, this can happen. Yeah.
Maybe I have a simple question. Just back to just 8.1 with
Okay.
SVMs, more like a general question too. So I was thinking about like when I was learning about SVMs and having kernel tricks, like for example, Gaussian kernels, and then we basically apply this kernel trick in the dual on the data points, and so that you don't have to explicitly compute the projection of your data points into like a super high dimensional space.
Mm-hmm.
And in the dual, that means I think you don't need to say write down any constraints in relation to that high dimension, which could be infinite dimension or something. But I'm just trying to wrap my head around what this means for the size of the LPs, the corresponding LP in the primal space, which I think we briefly touched on. Like I imagine if you have like a super high dimensional kernel, you would, and I imagine the size of LP would have to do with the number of constraints that you have. And I would imagine that somehow your primal LP would have a very large size, but somehow with infinite dimension, I would assume that would go to infinite size, but somehow that's still in polynomial relationship with the size of the dual LP. And this is, I guess, I didn't quite get this.
Yeah, I'm not sure if we're exactly talking about the same things. I guess, I mean, I'm not like a super expert here, so I might be like, maybe what I'm about to say like doesn't make sense, and what you're saying does make sense. That's quite possible. I guess this story with, I mean, this is like, okay, this problem here is like a little bit like, trying to find, the best fitting hyperplane in this like sort of expanded feature set where, you are using, okay, a degree 2 polynomial kernel. And, in this problem, we're like explicitly writing everything out. And so therefore we're like introducing, quadratically many new variables. And I guess, okay, wait a minute. No, I see, okay, I see what you're saying. So like here, let's think about it. We have like quadratically many variables. Let me write in white. But I guess we still have the same number of constraints, right?
Yes.
And yeah, so if we were, okay, good. So if we were gonna like do, I don't know, like a degree 10 kernel or something, we would have like maybe, I don't know, n to the 10 variables, but still like, I don't know, n constraints. And yeah, I guess like what we were just discussing, like, if you take the dual of this, you'll have, n variables. I'm running out of room here. You'll have like, the dual will have like n variables and like n to the 10 constraints. And somehow like this is usually a lot better of a situation like for solving, because typically like you'll always be, if you imagine like, I don't know, any algorithm, whether it's like a LP algorithm or any kind of optimization algorithm, usually like, maintain like a solution explicitly and then try to get like better and better solutions through some kind of iterative process. And so you usually be like writing down or like holding in your hand like a current solution. And so you'd much rather like that be like n variables. And it's maybe, better for you, or it's like more okay for you if your constraints are like very many. Because like maybe you don't like always sort of explicitly write down your constraints. You just like think about your solution and think to yourself, like, okay, I want to like improve it, or like understand if there's any constraint that's violated, or like some constraint that I should fix. And often if like you're in a pretty like nice algebraic situation, like you might be able to figure out like what sort of constraint to worry about next by some smarter method than just like, oh, I will now enumerate all the constraints, write them all down, and see how I'm doing on each one. So it depends exactly on how your algorithm tries to improve its current solution vis-a-vis the constraints or the things you're trying to optimize. But like, yeah, this is typically like a much better scenario than this dual one, than this primal one. Even though if like you didn't know anything, or you're working in like a perfect vacuum, you might be like, well, they're both of size n to the 10, so they're equally good or bad. Yeah, maybe I should have thought about like, or maybe I should have asked like you to, this problem over here asks you to like take the dual of some particular linear program and just think about it. Like, yeah, maybe I should have also done that for this one, like take the dual of one of these linear programs and think about its meaning. Although perhaps if you're like coming from a linear programming background, maybe, or I should say from a machine learning background, maybe you've thought about this already. But if not, that could be like a nice exercise for you.
Maybe just a very quick question. So when we say polynomial sized LPs, we mean both the constraints and the variables combined together. Like,
yeah, here I'm just being very simple. I'm talking about like the number of variables, the number of constraints, and even I suppose, to be like real theoretical about it, like the number of bits you need to write down all the numbers in the constraints.
I see.
This is like another probably like difference from like, theory and practice, right? Like maybe in practice, you'll just be like, well, all my numbers are just, I don't know, floating point with like 16 bits or 32 bits or something. And, if like some error accumulates, what are you going to do? We'll just proceed. And so there, you would only be probably interested in counting the number of variables and number of constraints.
I see. I guess my confusion earlier was, say in primal you have n constraints, in the dual you have a lot more constraints with higher dimensions. I was just confused, say, because in the slides we're looking at angle bracket k, and I thought it was only relating to the constraints. But I think, yeah, that makes sense.
Yeah, it basically means, well, I mean, the way I think about it theoretically is like, okay, the constraints, if you were to write them all down, would be defined by like a matrix with like, usually would say like m rows if there are m constraints, and n columns if there are n variables. And each entry is like a number. And so if each number you assume takes at least one bit to write down, then the total number of bits in the input will be at least m times n. So in some sense, the size of the input will always be at least the number of variables plus the number of constraints, or even the number of variables times the number of constraints. Actually, this is another like major like difference in practice. I mean, in practice, it's often the case that like maybe your constraint inequalities are very sparse. Like they might mention only a few variables. So you wouldn't like store your constraints as like a complete like m by n matrix, because that might be very wasteful, especially, you could have like 1,000 variables and 1,000 constraints, but maybe like there aren't literally a million non-zero numbers in your linear programming formulation. So the sparsity of these is also important in practice.
Yeah, so that just be then the constraints stored as some like oracle or something usually, like some like thing some yeah oracle you can question to see if like you actually violate any of the constraints or get that gives you the separation.
Yeah, actually, that's the one way to think about it. Like in the Oracle model, the separating hyperplane model. It could be like you have exponentially many constraints or infinitely many, but like you just somehow you don't write them down. You don't write them all down, but you maybe have the ability to question them. I was just thinking like more practically, like even if like, you have the constraints explicitly, like maybe you have like 10,000 constraints and 1,000 variables. It's just often the case that like many of the entries of the constraint matrix are zeros. And so you store them with like some kind of sparse matrix format rather than a full matrix format.
Right, that makes sense. Maybe we can do like question 8.3 actually, because I remember doing it, but not like actually getting everything. Maybe like I was like maybe there's a better way of looking at this. So 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 I was trying to come up with a good way of representing the matrix here and the matrix of constraints here, and it was somewhat complicated, and I'm not sure if that was like potentially the best. Like I basically did a little bit of a pattern match between this and the max SD cut kind of problem, and it seems super similar. So I was able to maybe make some inferences, but maybe perhaps we could do it in more like explicit detail.
Yeah, this cleaning up is sometimes important. Yeah. Well, sure. I'll write, you speak. So, yeah, what's
So
the LP?
let me, what is the
Original
LP
primal.
for the, just I forget exactly what the PC LP is. I'm just pulling it up. Yeah, so you're given, so this is the ILP that we're writing, or the full LP, I guess.
Yeah, we can start with the integer linear program, sure.
Yeah, so this is like, you want to minimize the sum of CV XV for XV in 0, 1, and XU plus XV greater than or equal to 1 for all UV edges.
Yep, okay.
We relax this one to XV being between 0 and 1.
Yeah. Okay, good.
Yeah.
So what's the next step?
We converted the equation form, and then
I don't always do that.
Oh, interesting. Because I was trying to do that, and then because that like followed the dual followed from there, but maybe we can.
It's not the way we talked about it in class, at least, I don't think.
Oh, in class we did what was it? We took the primal LP. We wrote it in terms of the inequality constraints. So a1 dot x less than or equal to b. What was this?
Yeah, I mean, it's something like, if we have 3x plus 2y is greater than or equal to 5, and like x plus, I don't know, 8y is greater than or equal to 3, and we're trying to like minimize, 6x plus 10y. And the dualization process is to try to like find some number lambda 1, should be non-negative, Such we like times this by this, and some number
Oh,
lambda
yeah.
2, such this is non-negative, such we'd like times this by this. And then like add them up, and hopefully we'll get something that looks like 6x plus 10y is greater than or equal to some number, like, I don't know, 12 or something. And then we're like, oh, if we find the best possible lambdas, that will give us like the best possible right-hand side here. And hopefully that
Oh.
right-hand side will be as large as possible.
Right. I guess I was just like looking at it like explicitly from the slides that where we formulated in terms of that. But yeah, we can think of it as basically c dot x, sorry, c dot x less than equal to some beta as the new constraints, right? And was that it?
Let's just do it like on, we can even just do it on like some little graph, I
Right.
suppose. Like, let's do it on this graph. There's 3 vertices. 1, 2, 3. Let's assume that all the costs are 1.
Right.
So then the minimum vertex cover LP is x1 plus x minimize x1 plus x2 plus x3 subject to
Right.
oh, 0 is less than or equal to x1 less than or equal to 1, 0 is less than or equal to x2 less than or equal to 1, 0 is less than or equal to x3 is less than or equal to 1, and x1 plus x2 is at least 1, and x1 plus x3 is at least 1, and
2 plus x2.
yeah, somehow my screen is refusing to scroll. Oh, there we go. x2 plus x3 is at least 1.
Right.
And I guess for this, like,
Yeah.
I'd probably say like, oh, I'm going to multiply this one by a half. I'm guessing here. And this one by a half. And this one by a half. And these are really 2 inequations or inequalities.
Right.
And if we want them all to be like greater than or equal to, this one's really like x1 greater than or equal to 0 and like minus x1 greater than or equal to minus 1. Got more of those. But anyway, I think I'm going to multiply this one by 0, this one by 0, all these ones by 0. And if I finally add all that up, I'll get, I'll get half x1 here, half x1 here. So I'll get 1 x1. I'll get half x2 here, and I'll have x2 here. I'll get half x2. I'll get plus x3. And then the right-hand side will be a half 1 plus half 2 plus a half 3. So it'll be at least 3 halves. So these lambdas, these are like our lambdas. Like these lambdas have certified that the minimum better be at least 3 halves. And I'm pretty sure that like in this specific instance, like these are the optimum lambdas and that like 3 halves is the true answer.
Right, that makes sense. Okay, so we would basically have to come up with like lambdas for each of the constraints here. And then the LP becomes the lambdas, the lambdas plus the lambdas times the constraints added together. That becomes the maximization problem then, right? So it becomes max lambda. I guess we have like, we can break this up into 3 constraints: xv greater than equal to -1, xv greater than 0, and xu plus v greater than equal to 1. And each one gets a lambda.
Yeah, so these are 3 different kinds of constraints. There's I suppose number of edges of these, there's like number of vertices of these, there's numbers of vertices of these. And it's quite nice. I mean, it's like a good practice to name like your lambdas with different letters for different types. So I might call these ones lambda sub uv. But like maybe
Right.
I'd call these ones with a different letter. But these
Mu
ones
or
are like
something.
sort of a little bit similar. So sometimes you might call them by like similar letters. You might call this like mu v, and like this
Right.
one, like I don't know, mu prime v.
I see. That makes sense.
This is like kind of a good life tip, just to I don't know, it usually works out well. I mean, it's helpful to have like different letters for like different like kinds of
Cool.
constraints.
That makes sense. And
Right. So actually, if I were to add all this up,
right.
what would be the coefficient? The coefficient on like x, I don't know, w, where w is some specific vertex.
So you'd have all the contributions from mu v and mu prime v. So
Okay.
so it'd be like mu v minus mu
w
prime
maybe.
w. Oh, mu w minus mu prime w.
Mm-hmm.
And then all of the edges or the neighbors of w that the edges that contain w, and for them you'd have lambda mu v. W v, where v is a neighbor of w.
Yeah, like really these kind of should be like sort of unordered. So it's like maybe
Yeah.
like sum over v, as you say, a neighbor of w of like lambda sort of vw.
Right.
That's right. So like when you add them all up, you'll get like all of this like, times xw
Right. That makes sense.
plus, and like similar stuff for every single w.
Yeah, that's right.
And then you'll get greater than or equal to, and what will go on the right-hand side?
So it'd be minus mu minus mu lambda, sorry, mu prime w minus mu prime w for the second term. For first term, it's just 0, and the last term it would be again lambda the total number of neighbors times the lambda v w. Is that correct?
Not quite. So actually the first, I mean, I'm imagining like you multiply all these multipliers against these inequalities and add them up. So the first thing I asked is like, what would be, like on the left-hand side, you'll have some linear combination of the x's. And I just asked you, what's the coefficient of this specific xw?
Right.
But now I'm asking on the right, I'm like, what is the total of everything on the right?
Yeah. Oh, I see. That makes sense. Yeah, so you probably get the total number of vertices times minus mu lambda v, because you have to sum all of them up. Is that correct? For the second equation?
No, I don't think so.
Maybe I'm getting something wrong here. So if I understand correctly, we're just like multiplying the mu's and the lambdas by these inequalities and then summing them up, right?
Yeah.
So for the first inequality, the xv greater than or equal to 0, all the mu v's will be 0 on the right hand side. So they don't contribute anything to the.
All the mu v's will be multiplied by 0. Yep.
For the second one, all the mu v primes would be I see. So this would be the sum of all the mu v primes for all of the v's in the graph, and minus of that.
Yeah.
And then that makes sense. Okay. Yeah. And then plus like all the lambda UVs where UV is an edge in the graph.
Yes, exactly.
Yeah, makes sense.
Yes. So like you'll have one inequality that has like this big old expression on the right-hand side and like this big old expression on the left-hand side, where in this left-hand side expression, so we only wrote down the piece that included x.
Right.
W.
Right.
But now we want this inequality to look like a lower bound on this, or rather a lower bound on this.
Yeah, yeah, we want a max over something like the so we'd have the max over the sum of all of the W's where the coefficient, the coefficient is this like coefficient that we have here. Is that right?
We're trying to make the left-hand side
Yeah,
literally look like identical to this.
I see.
So in order for that to happen, some stuff needs to happen. I mean, the lambdas and the mu's and the mu primes have to be really well selected.
Right, right. So we have to constrain the lambdas and the mu's to what would be?
Whoa, something weird's happening here. My pen.
All the lambdas and mu's should be positive. That's one of the constraints.
That's true. Whoa, something
And-
really weird is happening with my computer, but I'll survive. Yeah, every time I write, it like moves the letters a little bit.
No.
Well, we'll live. Yeah, all these have to be non-negative. That's true. Otherwise, this move of multiplying the inequalities by lambdas and mu's is not really legitimate.
Right. And then there's another like equality constraint
Yes.
where the equality constraint comes from the fact that what was the equality constraint? I guess the equality constraint is that the lambda, the mu's should the mu's should be I'm not exactly sure what the equality constraint is here.
Well, let me ask you a question. I'm going to circle something in blue and hopefully it'll.
Oh, I see, I see.
What do we want this blue circled thing to be?
Right. We want this to be like C.
What's like C?
CW.
Exactly. This should be
right,
exactly equal to CW.
Right, that makes sense. Oh,
and we want that to happen for every W.
Yeah. So.
And then what do we want to optimize?
We want to optimize the sum of the max sum CW XW. Right.
In the primal, we're trying to minimize
sum of
CW XW. But like, if we manage to get all these blue things exactly right.
Right. Oh, we want to maximize the right hand side.
Exactly. Yeah, we want to maximize this thing in yellow.
Right.
Because if we get all the blue stuff literally exactly right, then the left-hand side will be this original objective. And then whatever the right-hand side is, like the bigger the number is, like the happier we are, because we're like, oh, we just proved or certified that the minimum has to be at least this.
Right, that makes sense. Yeah.
So yeah, we're motivated to like make this right-hand side, which only involves the variables, as large as possible. Okay. So indeed, like we've got a new linear program where like the lambdas and the mu's and the mu primes are the variables. We have like a bunch of equality constraints, and we're trying to like maximize like this thing.
Right. That makes sense. Yeah. So
but then the task is, sorry, I was just gonna say, then the task is you're like, kind of gross looking, or at least one has to try to think about like, what does it all, mean?
I see. So this would be like the cleanup kind of stuff.
Yeah, like now you have to like kind of clean it up, or at least just like think about what's going on. You really want to like find, well, maybe like tidy things up if things can be tidied up.
Right.
And then like you want to like find some like story to tell, such that that story makes you write down this LP.
I see. Yeah, my intuition was that like there was, since we're doing the max vertex cover here, I thought that, minimum weighted vertex cover, like I was assuming that this would like be related to the dual of the graph, and then you'd be doing like some form of like max hover on the dual of the graph, or something like that, because something where you're selecting edges instead of selecting nodes.
It is definitely something like where you're selecting edges instead of selecting nodes. Yep.
It was similar to the
it's like a general
max
like.
SD cut.
Oh yeah, go ahead.
It was
Yeah.
similar to the max SD cut kind of intuition, where like you can think of like them very similarly, by like thinking about like the dual of the graph or something.
Yeah, another like a life like tip or fact is that like the dual of like something that involves the word cover will usually involve the word packing, as it turns
Okay.
out. It's kind of like a
Okay.
tip. So somehow the interpretation of the dual of a covering problem is usually a packing problem. So it's really just like a linguistic clue, but yeah, I guess when you're staring at this like new LP you've written down, trying to understand what's going on with it, yeah, it may be something to do with packing. Another thing to say is like, I mean, this sort of just occurred to me, but like, how one thing like we mentioned in class, it's like kind of relatively well known about linear programming is like, oh, we saw these tricks, like if you have a greater than or equal to, and you wish you had a less than or equal to, then you can just negate things.
Right.
Or if you have like a variable that's unconstrained in sign, but you wish that it was non-negative, then you can replace it with like a positive version, subtract a minus version.
Right.
And if like you have an inequality and you wanted to have an equality, you can like put in a slack variable and like these kinds of tricks.
Right.
This cleanup that like you often have to do is frequently like undoing those tricks. So you should like look in the LP you've written down and think like, does it look like the sort of thing where like somebody did those tricks and now I will undo those tricks? Because like the original form is conceptually simpler and these tricks were designed to just like put it into some mechanical format, but like conceptually you wish you had the original format. Like often with this like duality and cleanup, like you get to some expression or some LP and you like can maybe recognize that it looks like somebody had done these mechanical tricks to something that was conceptually more meaningful. So think about if you can like undo such things.
That makes sense. Yeah, that's interesting. I think this is like better. I was trying to like formulate this in terms of some matrix problem. I think you can, but the matrix is very undecipherable in some sense.
Yeah, I mean, in some weird way, like this method that I'm describing for taking the dual is like actually like a slower and more laborious way of doing the thing with the matrix where you just take the transpose of the matrix. But like I like doing it anyway because like it's like I feel like I psychologically understand what's going on, whereas like
exactly.
I don't know, like when I first learned this stuff, like, I learned it from professors that somehow just like knew how to like do duals and they just write down the LP and then they just like instantly write down the dual. And they just had like, I felt like they had like some like 7 rule algorithm that they were running in their head. And like, I was like, oh, do I have to memorize this algorithm? But like, eventually I finally understood that's like, it's very natural. You're just like trying to get the best certificate of like how good you could possibly do by basically combining the constraints. So then I was like, oh, I'm just going to do it the slow way every time because at least I'll understand it then.
That makes sense. Yeah, because I was doing it in the matrix and like it was like effort to put it in the matrix form, and then when you try and like then once you have the dual format, like then you have to like kind of like decipher it, which is much harder than like doing this, I think.
Yeah, hopefully this will be a more understandable way.
Cool. Thanks. That's useful. That was useful.
Okay, I guess I'll wrap it up about now. Any last minute questions? All right, well, then I'll see you around.